Today we're going to go over Chapter 26, Inference for Counts. So we're going to look at the chi-squared test, goodness of fit test. So we're going to ask, with this test, how closely do the observed counts fit the expected counts? So our example is, on sale in the school concession stand, there are a range of drinks from juices to sports drinks. The purchasing agent thinks each type of drink is equally favored among students. A sample of the purchasing data from the concession stand for the last 6 months is shown in the table. So we have it here with our lemon lime, kiwi strawberry, tropical punch, and grape. Is the purchasing agent correct? So with this, we want to state what we want to know. So are the types of drinks uniformly distributed, meaning equally favored among the students? So our null hypothesis is the types of drinks are equally favored among the students. Our alternative hypothesis is the types of drinks are not equally favored among students. Our assumptions and conditions. The data must be counts for the categories of each categorical variable. Numbers of students who prefer each flavor drink. The individuals counted should be a random sample. Although the sample is not random, I will assume it is representative of future sales of drinks. And all expected cell counts are greater than or equal to 5. The null hypothesis predicts 25% of 680 drinks, or 170, should be counted for the flavor. So 170 is greater than or equal to 5. So when you do these problems, you also want to have in your table those expected cell counts. So here we have our observed, and then in parentheses, we're going to have expected. That tells the reader what you want, and our expected, since it's equally distributed among the 680, would be 170 for each of them. So you need to name the test, just like we did with every other inference test. We're going to use the chi-squared goodness of fit test with 3 degrees of freedom. Our degrees of freedom are n-1, where n is the number of categories for the goodness of fit test. To find your test statistic chi-squared, you would use sigma of our observed minus expected values, all squared, divided by expected. And you do need to show the work for this. So to find our chi-squared test statistic for lemon lime, it'd be 159 minus 170 squared all over 170. Plus, for kiwi strawberry, it would be 198 minus 170 squared all over 170. Plus, for tropical punch, it would be 174 minus 170 squared all over 170. And then lastly, grape, 149 minus 170 squared all over 170. And this equals about 80 or 8.012. And that's your chi-squared test statistic. Now, you also need to obtain the p-value. And remember, if they don't give you a significance within the problem, you want to use an alpha level of 0.05. So to obtain the p-value is the area in the upper tail of the chi-squared model with 3 degrees of freedom. And that is above the computed chi-squared value. So this is the area here. Okay, the method 1 to find that area, the p-value, is you would go to distribution by pressing second in bars, choose number 8, chi-squared CDF. Your lower would be your test statistic, 8.012. Your upper would be 1E99 because you want a really big number. Your degrees of freedom would be 3. You would paste that in, and you get 0.04576. Another method is, in list 1, you put your observed values. In list 2, you put your expected values. You can go to stat and choose test and do chi-squared goodness of fit test. Your observed values are in list 1. Our expected values are in list 2. We put our degrees of freedom, which is 3. This gives you your chi-squared statistic, your p-value, and your degrees of freedom. This last part you can ignore. And what you need to do is still show the work for your chi-squared statistic, but you can get all the information here. So our p-value for this is 0.0458. So we need to make a decision and conclusion. We need a decision regarding the null hypothesis tied to the p-value and state the conclusion in context. The p-value is less than the significance level of 0.05, that should say. So this right here should say 0.05. 0.04576 is less than 0.05. I reject the null hypothesis. These data show evidence that the drink flavors are not equally favored by students. And to interpret the p-value in context, the p-value of 0.04576 means that if the drinks were equally favored by students, an observed chi-squared value of 8.012 or higher will occur only 4.6% of the time, or in only 46 out of every 1,000 samples. Which type of drink impacted your decision the most? Explain what it means in context of the problem. So kiwi strawberry affected chi-squared the most. Its standardized residual is the largest. And to find the standardized residual, you take the square root of its part of the test statistic sum. So more students preferred kiwi strawberry compared to what the purchasing agent expected. The purchasing agent should order more kiwi strawberry than other flavors. Now we're going to go to the chi-squared test of homogeneity. Here, we compare observed distributions for several groups to each other to see if there are differences among the respective populations. So how did the 2009 Rockville High School AP Statistics exam scores compare to the national results in the same year? So here we have the data. Is there evidence that the Rockville High School AP stat scores are significantly different than the national AP stat scores? The two populations are different. Our hypotheses. We need to state what we want to know. So we want to know, are RHS scores significantly different than the national scores? So our null hypothesis would be the 2009 AP statistics scores for RHS and the nation have the same distribution. Our alternative hypothesis, our 2009 AP statistics scores for RHS and the nation do not have the same distribution. For our assumptions and conditions, the data are counts for the number of students who received each score. Individuals counted should be from a random sample, but that is not relevant here since we aren't comparing other high schools or other years. All expected cell counts should be greater than or equal to 5, and that's shown in the parentheses on the next page. How you find your expected cell counts is the row total times the row column, the row total times the column total divided by the overall total. We need to name the test. We're going to use a chi-squared test of homogeneity with degrees of freedom. So our degrees of freedom is 4. So I will use a chi-squared test of homogeneity with 4 degrees of freedom. And so to find your test statistic is the same, is the sum of the observed minus expected squared all over expected. Now you again need to have your observed and expected values. So you do want to have a key. So observed and then expected is in parentheses. So you need to have your totals. So here for totals, you would take 14,353 and add 3 to that, and our total would be 14,356. And then 26,050 plus 13 is 26,063. 28,276 plus 14 is 28,256. 290. 22,283 plus 7 is 22,290. And 25,914 plus 6 is 25,920. Your row going across, you would add going across, and I'd get 116,876, and then 43 students took it at Rockville. Then my grand total would be 116,919. So to find my expected count here, for this first one right here, we'll do it over to the side. It would be your row total times your column total divided by your total. Okay? And that would be 14,350.72. And for this one, it would be 5.28. Now, observed counts must be whole numbers, while expected counts rarely are. Do not round. So you need to have at least like 2 decimal points for your expected value. Now you still need to find the chi-squared statistic here. So it's found the same way. So you'd have chi-squared equals, and we just start at our nationals that got 5. So we would have 14,353 minus 14,350.72 all squared divided by 14,350.72 plus, then you could go across and you'd have 26,050 minus 26,053.41 all squared, all divided by that 26,053.41 plus, then you can go to the last one where we would have 6 minus 9.53 all squared divided by 9.53. And this would give you a chi-squared statistic of 4.929. You do have to show this work, even though your calculator will find this value for you. You don't have to write every individual one. You can start with the first two, go to the last one. So to obtain the p-value and your chi-squared statistic, you want to input the observed data in a matrix in the calculator and run the test. So here I put my observed values in a 2x5 matrix. To find matrix, it's second in the inverse key on your calculator. After you input your values, you're going to go over to test by pressing the stat key, go down to C, which is the chi-squared test. Observed is going to be matrix A. It should default to that. Expected will be put in matrix B. Then you choose calculate. It gives you your chi-squared statistic and your p-value and your degrees of freedom. So that you don't have to do all your expected values by hand, you can go to matrix B and look at it here. However, notice because these are much bigger numbers, the 14,351, you need to click on that value to get it to at least 2 decimal places, since you don't see the decimal places, so make sure you do that. So we have our information here, our chi-squared statistic and our p-value and our degrees of freedom. So you're going to want to write that down in your notes. So our chi-squared equals 4.929, p-value equals 0.295, and my degrees of freedom is 4. So a decision and conclusion. So we're going to always use the significance level of 0.05. So the p-value is greater than the significance level of 0.05. 0.29 is greater than 0.05, so I fail to reject the null hypothesis. There's no evidence that RHS AP statistics scores differ significantly from the nationwide scores. The last type of chi-square test is the chi-square test for independence. One group is cross-categorized on two variables to see if there's an association between the variables. Are the variables independent? Is there an association between eye color and handedness? Here's the data collected from a sample of Rockville High School students. So the eye color is blue, brown, or other, and the handedness if you're left-handed or right-handed. We have our values here. So I have 10 students who are left-handed with brown eyes, so on and so forth. So state what we want to know for our hypotheses. Is there an association between eye color and handedness? Our null hypothesis would be there's no association between handedness and eye color, meaning they're independent. Our alternative hypothesis would be there is an association between handedness and eye color. Assumptions and conditions. The data accounts for the number of students in each category of handedness and eye color. Notice that's within context. For all these examples, everything should always be within context. The sample isn't stated to be random, but it is assumed to be representative of all Rockville High School students. All expected cell counts are greater than or equal to 5 and shown in parentheses on the next page. And you find those expected cell counts the same way we did in the previous example. So we need to name the test. We're using a chi-square test for independence with degrees of freedom 4. So you would state, I will conduct a chi-square test for independence with 2 degrees of freedom. Not degrees of freedom of 4, but 2. Now you do need to find your test statistic again. You will have to show the work to do that. So here, again, we're going through. You have to have your observed and expected values. So with this, we have observed, not in parentheses, and expected in parentheses. So you do it the same way. It's the total and the totals. So you would get all your totals here, add them up, and get your value for your expected values here. Again, you don't have to show the work to find your expected values. You can get them from your calculator. So I notice here I'd have 13.411. So for this one, it would be 13.411. Okay, we do need to show our work to find our chi-squared statistic by hand. So chi-squared is observed minus expected, so 10 minus 13.411, all squared, divided by 13.411. Let's do another one going across. 71 minus 67.589, all squared, all over 67.589, plus dot, 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 all the way to the last one. 26 minus 27.536, all squared, divided by 27.536. Now remember, your calculator, and I'll go over the steps in a minute, can find this for you. So if I look here, my chi-squared value is 2.244. So my chi-squared statistic is 2.244. Again, your expected values should not be whole numbers. Make sure you don't round to the nearest whole number. Have at least 2 decimal places there. So again, to run this test on your calculator, you put your observed counts in matrix A. You go to test, choose the chi-squared test. This should default as A and B. Choose calculate. You get a chi-squared value. So here, our chi-squared test statistic is 2.244. Our p-value is 0.3256, and our degrees of freedom is 2. Again, if you want to see the observed matrix, choose number 2 under matrices, and your observed values will come up so that you don't have to do all the work by hand. So we need to have a decision and conclusion. So the p-value is greater than the significance level of 0.05. 0.326 is greater than 0.05, so I fail to reject the null hypothesis. There's no evidence from these data of an association between handedness and eye color. And to interpret my p-value, a p-value of 0.326 says that if there is no association between handedness and eye color, an observed chi-squared value of 2.244 or higher will occur in about 32.6% of the samples this size.